So the first question, and before I open up the mic, I'm going to ask each of the panelists, and if cost was not your issue, but you had one magic wand to reduce power, and your goal is to get to the lowest power, but you have only one magic wand in one particular device or interconnect technology, where would you see it? And then this way, we'll put the emphasis on you on what sort of troubles you most, and what do you think is where the real opportunities lie in terms of reduced AI power. Do I? All of you have to answer.
Okay, I'll go first. That's okay. Well, I had a wish, if any photonic device that was reasonably good was right in the next to your 7 or 14 nanometer transistor. I think that would kind of solve everything. Right.
Okay. How close is next?
Well, we're talking on the same chip. Right.
Well, I mean, the same chip doesn't mean next. I mean, next is how close.
On the same chip, you could be a fraction of a micron or a micron.
Oh, that's kind of a long distance. You mean that would be enough to please you?
Yeah, that would be enough.
Even a micron?
Yeah.
And let me. Well, okay, we'll comment on those points.
One optical wavelength, you like?
Ming,
yeah.
You have your mic.
Only one.
Only one. And what's
two.
the biggest opportunity?
I need two. I think definitely capacitance of the receiver and wall plug efficiency of the source is very important.
Very good. Okay. And we'll explore a little bit more what they mean in the following questions. Peter.
Yeah. I agree with the previous speaker.
You're not allowed
but the one that I'm after, I mean, that we have been fighting for all the time, is a reduction of link losses. Improvement of the coupling efficiency, the couple light in and out, because that goes together with the laser efficiency. If you put an insertion loss of a grating coupler or another coupling element in front of your laser, you reduce the wall plug efficiency of your laser immediately. So also, like the responsivity of your photodetector, if you can make a more efficient coupler to your photodetector from a fiber to a photodetector. I'm talking in the case of not on-chip links. Reduction of such insertion losses is at the top of my head there.
Very good.
Well, I have a thesis to write about photodetectors, so obviously I think everyone gave the same answer, and I wouldn't go away from that. But if the magic wand is you can make a phototransistor like I showed with decoupled regions, I mean, that's even better than having it close by, right? If you could have one device where you've optimized everything, and that's just one magic wand, right? And
depends how far it is from a circuit. If you need a CDR to get to, like if you need a whole another interface between that device and your actual electronics, then all the power is lost. Like we saw that on that thing, like between the chip, which sources the energy, to your photonics, you lose many picojoules per bit before you hit optics, right?
Okay, very good. So, interestingly enough, no one on the panel mentioned better couplers to silicon directly.
No,
did you
Peter said, yeah.
Because in the link, out of 100 photons, how many do you think are lost and not useful? How many useful photons per do you actually have in a link, in percentage or any other way?
I went very quick over my slide there,
yes.
But I had calculated it, what the optical penalties are of going from a transmitter to a receiver. In our solution, it's about 20 dB.
Okay.
Excuse me, it's about 12 dB.
12 dB.
12 dB.
And some other, I mean, there are other processes available which are 20 dB higher.
Yeah.
And that's including the coupling of the laser?
Yes.
So about 12 dB. So about a little less than 10%, maybe 8% or so so 92 photons are lost out of every 100.
90%.
Something to think about.
Yeah.
So, Vladimir, to explore and again, if there are more questions, please, but to explore why do you feel that having it right next to the transistor, 1 micron or a fraction of a micron, is the most important thing?
Well, I would say the key is that it's very close to the circuitry that actually wants to send information across, right? as we've seen, like in this example that Peter was showing, if your switch chip is here, and then to get from it to the optics at the edge of the whole board, you need certain type of an electrical link protocol to send. There's a clock data recovery, synchronization. All this is extra overhead. If you had optics extremely close, you could think of the lambda as just another wire on a chip, right? And when we signal from one gate to another gate, we don't need extra synchronization. We don't need all these serializers, all these overheads. So if you had optics be sort of a natural device to the process, just like a transistor is, you would be able to eliminate a lot of this fat that basically goes now and kills the overall efficiency, right? I would say, even without thinking where the laser is. We don't currently typically, maybe in the latest chips that you look at nowadays, you start getting switch cap, DC-DC regulators on there. But typically, VLSI chips don't have any kind of source on it, even in the electrical sense, right? So why should we insist of integrating lasers on there? We could be bringing light from somewhere else, but really have all the rest of the devices intimately integrated with the source of the information or the recipient, right?
Very good. So to quantify that little bit, Chris talked about 10 attojoule detector. Now, if you look at the capacitance of a wire on a CMOS chip, it's about a couple picofarads per centimeter, which is about equivalently 0.2 femtofarads per micron, about that. So if you have a few microns of distance between your detector and your receiver, which is what you have to fight in many integration strategies, you're already at a femtofarad. And that means that from an optical perspective, from what you said, Chris, you're at 10 femtofarads of optical power if it's a 1 femtofarad detector. So that sort of kind of puts the onus of bringing the detector closer to the gain element. And I think the most exciting thing of Ming, of what you were saying, is not necessarily that you have a low capacitance detector, but that detector is right at the gain element. And I think that's what Vladimir is also saying. Yeah. Bringing that detector right to the gain element, to the transistor, is something that will...
I think that's what Chris showed us.
Chris, yes, that's what Chris showed. So I think that is perhaps the one of the exciting things that came out this afternoon.
So I'd like to take one step further and say, do you think there is a practical path to getting some of these photonic elements right next to the, say, 14 nanometer process? Or are we always going to be stuck putting one wafer on another, and then you have the few femtofarad via capacitance?
Well, I guess Peter can.
Yeah, I think it's really a cost question. 16 nanometer is very expensive per square millimeter. If I could choose, and if the money was not a thing, of course I would want to have the electronics monolithically integrated with the photonics, but I think the cost will be prohibitive. And another reason is that all the photonics are pretty large compared with the electronics, so they take also up a lot of real estate on that very expensive 16 nanometer process. So that's why I think we'll have to find maybe smaller copper pillars. Or I think that the method that Vladimir showed was actually very interesting because you had a via through the oxide, so you don't have the penalties of the capacitance. Yep. Well, but then again, I mean, also there is the cost because you bond two wafers together. Yeah. So your electronic and your photonic chip have to be the same size or yes, approximately. Yes.
So do the requirements of the serializer, deserializer, CMOS need to be exactly the same as the amplifier? Because you could imagine having your amplifier on, say, a bi-CMOS chip where they make really good transistors, but they're big because it's cheaper. But they're fast, they can get pretty low capacitance. And then you could have all the serializing, deserializing on a...
Actually, if you look at 28 nanometer even process FDSOI, it's as fast as your bipolar, if not faster.
Sure, but it's 28 nanometer.
Sure.
So it's expensive.
It is, but so is the bonding kind of, there's extra cost in everything that's not just printed, right? I mean, I would say there is some hope for monolithic as well. When people move to FinFETs, they ran out of resistors, for example. So based on customer demand, they actually had to add a whole thin film layer on top of a FinFET to essentially provide resistors for all the systems on chip. It's not purely digital application, but you need a radio, you need all sorts of things. People routinely add thick metal layers for inductors. You look at deep trench capacitors that IBM added to their process for caches and things like that. So if there is enough volume, and this touches again to what Peter was saying, like if you can find an application with enough volume, the foundry would do it. I mean, a few years ago, we demonstrated polysilicon photonics in a bulk platform. So you don't need to be super integrated with the front end. You could use that as a process module, but you need the foundry to recognize the market need for it to be able to do things like that.
So just to wrap up, I think the answer coming from the panel is that we started with maybe 50 femtofarads, went down to 20 femtofarads, maybe 10 femtofarads with some of the hybrid. Perhaps there's a path to a low single-digit femtofarads with through oxide vias. Beyond that, there seems to be an economic problem.
So maybe to switch gears to a more strategic question, I notice here on the panel we have a representative. I'm going to regard you, Vladimir, as a representative of the Photonics Manufacturing Institute funded by the federal government and the state government of New York, and where a vast amount of money is going to be poured into your institute. Congratulations. And on the other hand, we have a representative of a company in the field that says, we're doing fine already, we don't need your institute, thank you very much. And in fact, they're worried that you're going to maybe create some competition for them. Okay, so what is the mutual, don't tell me it's a mutual admiration society. What are the real feelings between the Photonics Institute and Luxtera? What does Luxtera think of these newcomers?
Well, I can actually maybe answer it in the unexpected way. We centered this session mostly about photonic links, okay? And granted, they're like the low-hanging fruit of photonic applications. But what I think what the Institute is about is something much bigger than that. And if you just actually even go into your Berkeley history, in 1990s, people started looking at bipolar processes, how to add an inductor to a process. Meyer and Nguyen did that. After you figured that out, you got the whole CMOS radio revolution. Okay? Then in BWRC in 2004-05, Nick Najad and Brodersen looked at how to build transmission lines onto ICs. Imperfect, but still there. And the whole millimeter wave, phase arrays, everything popped up from that. I think what IPMI is about is how do you get photonic devices of a vaster portfolio than just what is needed for the photonic link into close proximity with electronics, so that people can address a whole bunch of applications. We're talking about free space communication, LiDAR, sensing, photonic interconnects. But for anybody in the industry to start a company or an established company or a research group to be able to experiment with this, they need a streamlined process, right? Fortunately, Luxtera didn't open their process to people around them, right? So yes, they could have maybe ran an equivalent of it where people could be running ultrasound sensors, the LiDARs, and everything that's not their market objective, right? But so finally in the US, we have an entity that can do this. You just participate in an MPW run, you get a PDK, and you can design something that nobody has thought of, right?
Peter, any response?
Yeah, well, the thing that we are most afraid of if we would give our PDK away, because we think that's our crown jewel. That is the library of devices. We have been working on that for 15 years almost. We have made those grading couplers and devices with all these efficiencies that we have. So we are very concerned if that would be made public and available to everyone.
I would actually argue that really there's much more going on in the know-how. I mean, having built a lot of photonic links and about how you stabilize things around. So I think giving a PDK, I don't think it's opening up a little bit, but I don't think it's opening up as much as you think. Because there's a lot of built-in know-how. How do you use these devices? And of course, you can always offer a base PDK, and then a more advanced devices are going to be sort of on the part. And actually, that's going to be in the IPMI as well. There will be a base PDK and process description for everyone to use. But of course, every company can pitch in their specialized device for that process, which anybody can insert as an IP if they want to build a more advanced part. So if I have a super modulator, yeah, I will be able to add it as a standard cell offering. People will be able to license it, right?
And at the end of the day, I think you're a fabless company.
Yeah.
And so,
Yeah,
the investment in fab stateside, I think, is a good thing in the long run for
the other thing,
people who have.
I would say
design.
it's definitely not endangering the commercial entities like Luxtera, because keep in mind this is a prototyping foundry. Nobody can run a wafer lot per week, through CNSE. At like 1,000 wafers per year, because that foundry just cannot, it's not the model. So someone who wants to commercialize would have to contract some other foundry and start negotiating how to port the process, things like that. So I think it's more spearheading our general thinking, how do we build electronic photonic systems in a wide variety of areas, and then maybe doing some commercial efforts on top of that. We cannot endanger it, we can just help the commercial entities. Yeah.
Yeah, I agree, because that's actually, we have been approached also by other, before the IPI, by other research entities. They wanted to work with us, but the problem is we develop a process there, and then we have to port it again to a real production place, and you have to pay twice.
Yes.
We want to go straight to the source.
Yeah. So maybe just going back, this is a manufacturing question. I wanted to point out some sort of a white elephant in the room that we haven't considered here. We did talk about data centers, right? But we always looked at the link as being on all the time. What in fact happens in these data centers is that links are on roughly 1% of the time. Right? So you look at all these optical connections, the way there's contention in the optical network, really the servers cannot push enough. And actually they are, within the rack, those switches are heavily oversubscribed. So you basically end up leaking a lot of laser power into the network without sending many bits. So that factor of 10 picojoules, or whatever we had on the optical, and actually, unfortunately, even the electrical links from the host switch all the way, they're on all the time. Right? So if you wanted to actually save quite a bit of energy, actually 2 orders of magnitude in the actual data center, you would first think about how to do data proportional links. Right? Shut everything down. How do you build your laser backup? And this is one interesting thing about the LEDs, because if you're not running, you just shut them off. So it gives you some ability for fine-grained power management wherever you're going. Right? That's one thing that maybe is worth pointing out.
That's another source of wasted photons.
Yeah, how do you recycle the photons, basically, if you're already
is a possible answer to that just to add more optical parallelism so you don't get stuck in the switch?
I don't think it's as simple as that, because applications, actually one thing that's happening, you may be able to help by reducing the latency through the network, because it's really about people who are injecting traffic in. If the latency is too long, let's say a processor doesn't have enough of a depth of a queue for that many outstanding requests. So if you have a fat pipe, the processor can fill like 100G or 400G, but it takes you 10 microseconds or a millisecond to get across the network and back. Processor doesn't, it's basically Little's law. You're pumping in enough bits, but you don't have enough memory to hold on all your requests and then reservice them when the data comes back. Right? So then you're using only like a little fraction of the bandwidth effectively, and the rest you're just waiting for stuff to come back.
So we've talked about wasted sort of bandwidth, not really using it effectively. We've talked about losses in the link and couplers. Peter, of your link budget, let's talk a little bit about the transmitter. So how much of your link budget, or penalty, shall we say, is associated with an imperfect transmitter? Tell us a little bit about that.
Actually, what we found was that our transmitters are close to perfect.
You have a 4 dB. You have a 4
well, yeah,
dB.
If you look at dispersion penalties, but yeah, we have 4 to 5 dB extinction ratio now.
Yes.
With just the designs that we have, without doing anything special. Of course, we optimize our modulators for the best OMA, optical modulation amplitude. So that the insertion loss of, that is the kind of the interplay of the insertion loss of the modulator and the extinction ratio. But sitting on that optimum brings us at 5 dB. We could make it higher, but then the insertion loss will get higher.
So in your case, would it be 2 dB maybe?
Insertion of the modulator, yeah, it's about
2 to 3
2
No,
dB.
no, no. The penalty associated with the imperfect modulation.
Well, that's insertion, right?
Not necessarily.
No. There's the penalty because of the extinction ratio. Let me, yeah, I have to look it up.
I guess my point is that out of the 8% of photons you're not wasting, assuming you have a perfectly used link to begin with, you're also maybe losing another few dB of that, maybe half of that, to an imperfect transmitter.
Oh, yeah,
so
yeah.
when you're down to sort of the useful photons in these links, it's actually a very low fraction of the total photons that you're pumping in.
Yeah, that,
And-
you mean
and,
the extinction ratio penalty.
That's
I
correct.
believe it's about 1.3 dB, if I'm not mistaken.
So that's a very good penalty.
Yeah.
It's easy to get to 3 dB if you're not careful.
Yeah.
Yeah, yeah.
Can I ask a question also? So while we are talking about transmitters, and so in the research community, you see lots of people use tiny rings to save power. But in commercial product, it seems it's all the opposite direction. You see this convergence at a certain point?
Well,
Good
we
question.
have been looking at rings extensively, but we see, of course, the issue of the control. I think many people have been working on that. That is good. But we saw actually also some other issues. That is that the interplay with the light source. Laser diodes have a phenomenon that's called the mode hop. So that is when the wavelength suddenly jumps with like half a nanometer. If you have a beautiful ring with a control system, but the wavelength is shifting of your laser, is shifting with half a nanometer, that control system needs to reteach, and you lose data for a while until it finds back where it needs to be. So that was also a reason, because we have tested a lot of laser diodes. There is no laser supplier who is immune for mode hops, even for off-the-shelf mature laser diodes.
That's because the diode's sitting on top of a hot chip.
That's
Right.
not coming from that.
I mean, they're not naturally mode hopping. I mean, there's some cause for it, right?
Yeah.
So I think if you put a laser in the hostile environment, you do get these kinds of problems. Maybe if you move the lasers out of it, there is a bit of a different view.
Well.
So you're saying really it's environmental, and perhaps if you are able to get the right type of light source, then you might be more open
That is
to
why
lower energy, fundamentally lower energy
Yes,
transmitters.
yes,
I see. Any questions from the audience? Any other questions?
Yeah, there is one.
Yes. Could you speak up, please? Thank you.
I'm from Applied Materials, and from an equipment company standpoint, I have a key concern in terms of what are the material map that you really have in this photonics. From my understanding is that pretty much all the material is pretty conventional. Silicon, you have some oxide, you have germanium, and that's it. And I try to understand what, from a more strategic marketing standpoint also. Basically, we have Moore's law for electronic portion of it, but the roadmap for photonics, really, there is no dimensional shrinking. It's a constant dimensional, but we emphasize more on the bandwidth. So my question really is, when do you really see that the electronic and photonic roadmap crossover really is? And talking about cost, right? We have to have a really strong value proposition to switch a portion of an electronic to the photonics. Do you see that happening soon? And also, do you see that that happens with more materials involved?
Okay, I can try that. I think it strongly depends on the application, right? If we're talking only about photonic interconnects, I think the jury is still out which approach will make the most sense. You have everything from die-to-die bumping to purely monolithic on one die to this 3D. These things are trying to push the performance up. We'll see what wins. But I think definitely it would be useful to get these photonic devices as close to the transistors as possible. One misconception, though, is that even if you look at very short reach chip-to-chip type links, things like that, if you're using even a moderately big serializer like 4-to-1, 8-to-1 with a little bit of a timing circuitry and driver, already those transistors, even in 20 nanometer or 14 nanometer technology, the size of them are actually comparable to your photonic device. I'm not talking about, maybe Mach-Zehnder module, like these ring-based photonics and things like that. So, people think photonics doesn't scale, but actually the collection of transistors you need for some function like that is actually not trivial, right? So we will be, and in fact, if you look at FinFETs and things like that, people are backing off for energy efficiency to like a reduced pitch and things like that. So transistors are no longer scaling as we used to see them. So I think there's maybe an opportunity here as transistors are slowing down and that CMOS development process is extending, that maybe photonics can sneak in. Right? That's my hope, but I don't know if it's going to happen.
Anyone else like to?
No,
from a
that's
commercial
pretty
side?
much in line with what Vladimir said.
I mean, from the commercial side, it's very clear. Sort of, there's been a steady penetration of photonics into the electrical link, and that's basically bandwidth distance driven, and that goes back to the 70s, the 60s, and just as the laser diode was invented in the 80s, that really started seeing a very definitive curve over the last 30, 40 years of penetration bandwidth distance, and that bandwidth distance is about 100 gigabit per second meter. And that product, if you exceed that product, you go optical successfully in the industry. And now where that hits the chip interface and when it gets on, will we have to go below this metric or above it? That's unclear, and that's because of the manufacturing and other points the speakers have made. But at least from the outside in, it's been very, very steady. So I think that ends our panel. Let's thank our panelists and speakers once again. And Professor Vladimir will give some closing comments.